Okay, so in the last video we talked about covalent, 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 but this section is about ionic and covalent. So now we're going to talk about ionic compounds. So we use the periodic table to figure out how many bonds an element would make. Well, we can also use the periodic table to tell us what the charge of an ion is going to be, so long as it isn't in the middle. We are going to talk about the slices of the bread. The meat is going to be for the next section. So we're going to nibble on the edges here. So in the next section of the class, we'll talk about what we do here. But the periodic table does not help us with this. This falls outside of valence theory. This stuff we're good. Alright, so remember, emptying a valence shell or filling it does cause stability. And I kind of showed a little bit of this in the very first video of this section. And so when we were making covalent compounds, we were just filling valence shells. You can't share electrons away. You can only add electrons by sharing, right? You're bringing in more electrons, you're sharing. But with ionic compounds, you are taking those electrons as your own, or you are just giving them up. You're just getting rid of them. You're taking, or you're taking, or you're sending, right? So, someone's making the call, someone's answering the call, right? So nonmetals are going to pick up electrons, become anions. Metals are going to dump electrons and become cations. So metals are to the left. They have a shorter trip to empty than full. Nonmetals are to the right. They have a shorter trip to full than empty. And so you couple that with the electronegativity difference, so the fact that metals are just going to take electrons because they're more electronegative, and metals are going to lose them because they're less. Well, they're also going to be stable because they're going to take electrons till they fill up, and these are going to be stable because they're just going to lose electrons till they're empty. In the valence shell, anyway. So, remember that ionic compounds, just to refresh your memory, are going to be made when it's a metal and a non-metal. And we're going to build on these compounds more in the next section. It's all about them. But this is kind of an introductory. So the metals are going to empty the valence shell. And they're going to become cations because they're going to have a plus charge. The nonmetals are going to fill their valence shell. They're going to take on more electrons to do this. So they're going to be anions because they're going to have a negative charge because they gained more electrons. They gained negative charge. It's like they took on debt. Metals dump debt. Suddenly you don't feel bad for the metals, right? You're like, oh, they're getting their electrons stolen. Now I'm like, no, they got their credit card bill stolen, and then the non-metals for some reason paid the stolen credit card bill. Okay, so everything from lithium on down has one valence electron. Guess what they do? They dump one valence electron. These all become cations with a +1 charge because they have one valence electron to lose. Beryllium, magnesium, calcium on down, they're going to lose 1, 2 valence electrons to empty out. So these are going to be +1, +2. These are all going to be +2. Aluminum is going to be a +3. Everything else in here we'll talk about later. It's a mess. So +1, +2, +3. That's all we got to work with right now. On the non-metal side, these are going to absorb electrons. These are going to pick up electrons. The halides, the halogens, they all need one, and then they're full. So they pick up one electron, -1 charge. Oxygen, sulfur, selenium, tellurium. Who doesn't work with polonium, right? Hat tip to my Russian KGB friends out there. If you don't know what I'm talking about, look up Russian spy polonium, and you'll know what I'm talking about. I'll just tell you. Why not? So they poison the guy with polonium. As you can see on your little periodic table, it's radioactive. So this guy died of cancer very suddenly. And he said, I was poisoned. And they're like, oh, I don't know. And so then this was in United Kingdom. and so the MI6 or whatever they are, their guys went around and they actually went with a Geiger counter and they figured out where it happened. They traced it back to a coffee shop. So, Russian, they don't actually have KGB anymore, whatever they are now, FSB or something. Poured polonium into his drink, he drank it, he died from radiation poisoning, and he was shedding radiation everywhere he went from that point on. And so they're like, oh, he went, he sat at this table with that coffee, he drank it on this side of the table in this chair, and then he went to this store, looked at this book, used this stall in that bathroom. Like he took this bus, like they could trace all of it with a Geiger counter because he was shedding the radiation off his body, leaving it behind. Obviously not enough because it still got him, but so that really happened. And so that's your polonium story for the day. Story to tell just about in every corner of this periodic table. For example, boron. It's the most unfortunate element on the periodic table. Do you know why now? Do you know why boron's the most unfortunate element on the periodic table? I didn't talk about it in the last video, but it's a non-metal. It wants to make 5 bonds. It only has 3 electrons. It can only make 3. You gotta buy in. You gotta buy in on your half of the bond. It can only buy in on 3. It can't get 8 electrons around it doing that. Poor boron. But anyway, we're talking about ions in this, so take your sob story somewhere else, boron. So oxygen, sulfur, selenium, tellurium, polonium, they're going to pick up 1, 2 electrons to fill. They're 2 away, so they're going to be a -2. Nitrogen, phosphorus, arsenic, antimony, they're going to pick up 1, 2, 3. They're going to be a -3 ion. And then carbon, you're like, it's 4, what does it do? The answer is it doesn't tend to form an ion. It'll typically form a covalent compound. But if it does become an ion, more often than not, it is an anion. And so it will be a -4. But you don't see that very often. And so carbide compounds, like calcium carbide, you can actually use that. It's so reactive. It doesn't want to be an anion so much that you can actually use that process to light water on fire. So or ice even. So I worked with a guy, and he would teach engineers chemistry, and he'd like to mess with them in lab. And so he'd get some calcium carbide from the stockroom and a thing of ice. If there's a lab that used ice, he'd wait till there's a lab that used ice. He'd be like, hey, did you guys know that ice is flammable? And they'd be like, what? No, it's not flammable. And then he would have it palmed on his glove. You definitely don't want it on your hands, but you have a glove. And he would just kind of like casually like sprinkle it on there. And then as he grabbed the lighter, and he'd come back with a lighter, and he'd light it, and poof, because it was producing, it was stripping hydrogen off of the water, and it was making oxygen gas and methane, and so it would actually light on fire. And so all the, everyone knew he was pulling a trick, but he would try to make him figure it out. He would tell him eventually, but he'd like to mess up with them. All right, so non-metals are going to fill their valence shell. They're going to have a negative charge. Metals are going to empty their valence shell. They're going to have a positive charge. However many electrons they need to fill their shell, that's their negative charge. However many electrons they have to get rid of, that's their positive charge. That's all there is to it. So, how do we draw the Lewis structures? Well, if we have something like I don't know. Let's do calcium and sulfur. All right. Well, we got a metal, we got a non-metal, right? So we have an ionic compound. Well, I'm going to draw the atoms first. So these aren't going to share electrons. These are going to have transferred electrons. It's an ionic compound. Calcium has 2 valence electrons. How do I know that? Periodic table, right? 1, 2. Sulfur has, let's count sulfur out. 1, 2, 3, 4, 5, 6 electrons. So I'm going to draw that. So there's 6. I went a little bit cowboy with it. So let's slow it down. 1, 2, 3, 4, 5, 6. Okay. Now you might be tempted to start drawing lines here, but I want to be clear. No lines. This means they're sharing electrons. This, right here, being an ionic compound, means no sharing electrons. No sharing electrons, no lines. I see this all the time. So what does that mean? The electrons are transferred. So this electron, it isn't going to share. It's going to move. I don't know why I drew 2 sulfurs, by the way, right? There's only 1. Thank you for pointing that out. All right, and so the second electron is going to move over here as well. And so sulfur is going to be surrounded by 8 electrons now. It's going to have 4 lone pairs around it. Calcium's going to have none. As it lost that pair of electrons, it became a +2. And as sulfur gained, it becomes a -2. So 2 minus. 2 plus 2 minus. Now, if you must do something, you can draw circles. I won't make you. Be aware that I think this will be the formatting you might see in like exam questions, or the kind of weekly check-ins, or what are they called? They're not quizzes, even though they're really kind of like quizzes. Concept checks, yes. I totally didn't just scroll my Moodle page to see what they were called. I know my Moodle page so well. So this is what we do. So they're ions, so they're not sharing electrons. So what is holding an ionic compound together? Well, it's the same thing that holds an atom together. The negative electrons are attracted to the positive nucleus. Well, the positive cation is attracted to the negative anion. So they're not held together by shared electrons. They're held together by the opposite charges being attracted to each other. So the opposite charges attract. And so sulfur's like, thank you for the electrons. Why are you still here? And calcium's like, I'm stuck. I can't get out of here. So, you can dissolve in water, maybe. There's some tricks you can do to separate the ions, but generally, salts are really hard. Unless you use some sort of chemical trick to get them apart. You can't just melt a salt. It's really hard to, like, break a salt up sometimes. They're very, firm, because this is a strong attractive force. It's really binding them together. Whereas covalent compounds, those shared electrons kind of rubber band. And so they can kind of move, and they move around. These are just like spheres that are just stacked into cubes. That's what you have with an ionic compound. So they're not as exciting chemically. They're not like, a very exciting movement. But in return, you get to draw not very exciting Lewis structures. So you just move electrons till one side has 8 dots and the other side has 0. But you could have a situation where you have multiple cations and or anions. And so let's look at that. And that'll be the last thing we do in this video, because we're going to build on this more in the next section. But, if you have something like, maybe instead of calcium and sulfur, you have calcium and chlorine. And it's going to take 2 of those chlorines. You don't have to know why yet. We'll talk about that in the next section. Alright, and so we're going to draw our Lewis structures. Boom, boom. Now I have two of my non-metals. I was just thinking one step ahead earlier when I drew 2 sulfurs. Also, I wanted to make sure you were awake. And any other excuse I can think of, I'll use right now. So, you look at this and you go, okay, I've got to draw this Lewis structure, right? First thing you think is, well, okay, maybe I'll draw the atoms. That's a fair thing to do first. But then you got to go, is it ionic or covalent? Because that is a big fork in the road. Because if it's covalent, we would draw lines. But it is ionic because we have a metal and a non-metal. So no lines. I hope the little thumbnail preview of this video just has me pointing at this right here. I hope this is it. I hope it's just me pointing at no lines. No lines! Alright? So what do? Well, chlorine needs 1 electron, right? It has 7 valence electrons. It wants 8. So we're just going to move 1 electron to each chlorine. Now they are going to have 8. Calcium will have none. This is going to be a -1. This is going to be -1. We don't write the 1. If you do, cool. The professionals don't, though, because we're lazy. And calcium's a +2, just like before. And you can draw your little circles. I don't actually care if you draw your circles. I'm just staying consistent with the class stuff. They don't have to overlap. They don't overlap. That was a mistake. But that's it. That's the Lewis structure. So, be aware, Lewis structures for covalent compounds are different than ionic. They start the same way. But what do we do with these dots? Do we turn them into lines, or do we turn them into dots that are just hanging out? So these are transferred electrons. And so we have charges that are opposite. And I'm going to point out one thing. We're going to talk about this more in the next video. But you'll notice I have a -1, a -1, and a +2. So I have minus, plus 2 minus, that charge equals 0. Same with the example I did before. And that's going to happen with every single one of our ionic compounds. But we'll talk about that more in the next video. It's just a little teaser for you. Alright, so you should know how to draw Lewis structures for ionic compounds. You should know that you need to draw a Lewis structure for an ionic compound, and then how to do it. So no lines, right? No lines. I don't know if I've been clear about that yet, right? Maybe, you know, I'm gonna double box it. No lines, right? But only when it's ionic. If it's covalent, lines. So you're gonna end up with an anion with a full shell, cation with an empty shell. Or maybe multiple anions with full shells, or multiple. All your cations should be emptied, all your anions should be full. That's what it comes down to. Alright, so in the next section we will talk about naming this guy, and if I give you the formula, you'll be able to name it, and if I give you the name, you can give me this formula. So that's where we're going with it. So a little more detail with the ionic compounds. But that is the next section's problem. So for now, just make sure you're comfortable with the Lewis structures, and you know when you have an ionic compound, when you have a covalent compound. And then when you have a covalent compound, is it polar or nonpolar? When you have an ionic compound, do you have a polar or nonpolar ionic compound? No, because you always have maximum electron discrepancy. There is no sharing. It's not like, oh, are they equally or unequally having the electron stolen from them? Of course it's unequal. That's how it works. So that doesn't come into play here. Alright, so this will be the last video for this section. As always, you know, if there's something that's unclear at the end of these videos, there is a help forum on the Moodle page. I make sure to subscribe to them. So if you post in there, I'll get an email letting me know, and then I'll pop in and I'll answer it. And odds are someone else probably has the same question. So very efficient way of getting help. Highly recommend it. Alright, so we'll have one more section this week if it's the summer class. I'm not sure what my fall will look like. But yeah, and that section will build upon what we did at the end here.